Hello, my name is Jacob Tuttle. Together with my colleagues at Griffin Open Systems and the University of Utah, I'm grateful to have the opportunity to share with you today a little bit of the work that we've performed in the development of a long-term hybrid AI expert combustion optimization system for coal-fired electricity generation, NOx reduction. Beginning with a little bit of background on this topic, over the last decade and maybe a little bit longer as well, we've seen an ever-increasing concern for climate change of the United States, individuals within the United States, as well as those globally. This has had a number of impacts to numerous industries, but particularly in electricity generation, we see that this has resulted in kind of a paradigm shift in the identity of electricity generating sources, providing power to the electrical grid. And we see that since 1950, predominantly fossil fuels of coal, natural gas, and petroleum have been increasingly added to generate electricity for the United States. However, in about 2008, we see this shift in a number of retirements, and especially of coal, with natural gas making up a large portion of the difference, or what has left the grid, but also a large increase in the amount of renewable energy. And what this has resulted in is the remaining fossil fuel generators on the grid having to entirely change their operating practices. The reason for this is that renewables, particularly wind and solar, are highly intermittent, meaning that you can't really control how much power they're generating at any given moment. We're kind of at the mercy of how much wind there is or how much solar is visible to solar panels. And because of this, those base-loaded or dispatchable units, such as coal and natural gas, have to make up the difference in supply and demand. What we're looking at here on this slide is a 7-day load profile of a coal-fired power plant. And you see how the generation level is rarely ever constant over this 7-day period. There are multiple days where the unit never actually achieves a steady state. It's constantly ramping and changing load in order to make up that difference left by renewable energy changes, as well as changes in changes in demand as consumers and individuals change the amount of power that they need. Operation like this was never intended for a lot of these units, which were built in the 70s and 80s. At that time, especially coal-fired power plants were designed and intended to operate at more or less full load constantly, never changing load unless they needed to come down for maintenance. So to see units operating in this manner is very different from what we ever expected them to be capable of. But with this comes a long list of new operating challenges that need to be addressed. So what we, in our project here, have attempted to do is develop a combustion optimization system which utilizes artificial intelligence in order to improve the performance of the unit while operating in this new paradigm or this new regime. Our focus in this particular study was to use our combustion optimization system to minimize NOx emission rates, while also addressing other operating conditions at the power plant. One of the major focuses of our study here is to perform this evaluation over a significant period of time. There exist a number of studies which have been done for the short term, a matter of days, but it's important to understand how these systems, combustion optimization systems, will affect performance over years, as that's really where they will contribute to performance of such stations like this. And so we developed this combustion optimization system and evaluated over a 2-year period, while focusing on NOx emission rates, but also addressing other unit circumstances as they arose. And so our system, when we look at a coal-fired power plant, there are numerous systems which are each on their own complex with numerous interactions amongst one another. But what we did with our combustion optimization system was really focus on the combustion furnace itself. So this number 6 area, the fireball, and 5, the wind box, which if we can zoom in on that segment of our schematic, we see that there are a number of various inputs to which control combustion itself. Really what all of these do is control airflow, the amount of air which enters the fireball and what points, as well as fuel flow into the system. How air enters and where has a significant impact on the formulation or generation of emissions, such as nitrogen oxide or NOx. And so with our combustion optimization system, we want to identify, using artificial intelligence models or neural networks in this case, the best configuration of air and fuel into the combustion furnace to minimize the generation of NOx. The tool that we really used within this application is known as the Griffin AI Toolkit, provided by our project partners, Griffin Open Systems. The Griffin AI Toolkit was a valuable tool to use in our project here with its visual programming interface, which we see right here, allowing rapid prototyping in a no-code to low-code environment, enabling us to work directly with engineers on site to develop this enclosed loop. And so with this platform to develop our combustion optimization system within, we wanted to first identify the best data-driven modeling method to use. We considered support vector regression models, random forest, kernel partial least squares, and artificial neural networks. Each of these have been proven in many different applications to be effective at making predictions after training on operational data. And what we found in our situation was that for our training set and in our validation or our cross-validation set, focusing on the root mean squared error prediction, support vector regression and random forests were actually quite accurate. However, when these same models were applied to unseen validation test data, there was a significant decrease in performance. When we looked at artificial neural networks on the cross-validation set, they weren't quite as accurate or didn't perform nearly as well as the random forest or SVR models. However, on the unseen test data set, performance was similar, meaning that in our situation here, we could expect it to extrapolate better and provide more robust and stable control of prediction of the unit. So we opted to use artificial neural networks within our combustion optimization system. As you see here on the unseen test data set, the artificial neural network was 20% more accurate in predicting NOx emission rates than the SVR or random forest models. So with this identified, our combustion optimization system takes on this form roughly shown here, with 3 major segments of processing. The bias controller portion of the system, which actually implements closed loop control of those various combustion parameters, airflow and fuel flow into the system. Then that's the major portion of the combustion optimization system, or COS. However, in order to keep the system current and representative of the unit in real time, there's also a data acquisition portion of the system, which records live operational data in real time, and then a retraining segment that continually retrains these neural networks periodically to ensure that they remain up to date with any changes that the unit may experience. All of these systems or these subsystems together work with one another to result in our full combustion optimization system. With that in place, the way that we actually optimize using our neural network models is through particle swarm optimization. So what's advantageous about this is neural networks are not necessarily convex, nor are they continuous in a lot of circumstances, simply because of operational differences of changing mills or things of that nature at the power plant. And particle swarm optimization can handle these discontinuities and non-convexities by taking numerous guesses across the model itself, or the search space being the objective function, and then slowly gravitating towards the optimal solution. And so using particle swarm optimization in this manner, we're able to identify the best configuration of airflow into the combustion furnace to minimize the generation of NOx. So what we were able to see over the course of doing this was that in our 2-year period, beginning from our baseline, which is this solid green line here, quarterly, on average, NOx emission rates decreased across the unit's load range, where during our final quarter of evaluation, you see that across the load range, unanimously, NOx emission rates were lower during that quarter. On average, this is a 22.5% decrease in NOx emission rates, which we're very happy about. Furthermore, we were able to see that the system was able to achieve previously unseen NOx emission rates. What I mean by this is that the gray cloud that you see here are observations of NOx in the historical data. These red dots are observations from that final quarter of 2018. A lot of this operational area is not seen in the historical data, meaning that the neural network is able to push beyond what the data that it was trained on to realize new best performing configurations. Furthermore, I mentioned we were going to address other unit circumstances as they arose. One situation which we encountered were high temperature exceedances of steam temperature within the unit. This has the capacity to significantly harm the unit, lead to unplanned outages and other adverse situations. And so what we were able to do with our combustion optimization system was address some of these by implementing expert logic. We're able to identify a specific parameter within the unit, which helped to better control steam temperatures. And comparing 1 month without this control, to which we developed this expert logic, and 1 month with, we're able to see that able to decrease the number of high temperature exceedances by nearly 90%, which greatly contributed to the operating performance of the unit and the system. This also helped to increase the service factor of the system. We actually implemented these changes right here during the second quarter of 2018. And we saw from that point forward in the final 2 quarters of evaluation that our service factor of the system was above 80%, which tells us that operator acceptance of the system was high, and that our system is more likely to further contribute to advances and improvements in operating performance. In conclusion, we were able, through our project here, to identify artificial neural networks as the best model selection in this circumstance for predicting NOx emission rates. And through use of this combustion optimization system, able to decrease NOx emission rates on average 22.5%, compared from our baseline quarter to our final quarter of evaluation. Also, while performing this, able to reduce, while realizing this decrease in NOx, we were also able to decrease the number of high temperature situations or exceedances which were observed in the unit, which greatly helped to increase the service factor of the system and further realize benefits due to system usage. So I'd just like to thank the power plant which we worked with, as well as my colleagues and our funding sources. I have some contact information here. If you have more questions, feel free to contact me, and I thank you all for your time.